Hey guys, and welcome to Barron's Chapter 6, which is definite integrals. Alright, so this is really similar to anti-differentiation, and since I'm assuming prior knowledge of how to do that, since that was one of the previous chapters, let's just jump right into it. Definite integrals are nothing but anti-differentiation with numerical values attached, and then we just plug them in at the very end. So let's just see how this works for ourselves, right? So here's example 1. Now this is a nice and simple one, just to get acclimated to what will go on. So an integral from -1 to 2 of 3x squared minus 2x dx. Now all we do is first we anti-differentiate this normally. So once we anti-differentiate, we find it's x cubed minus x squared. Now what we do is just put a bracket around this and put this from -1 to 2. Now we just plug in a 2 in there, and then we get 2 cubed, which is 8, minus 2 squared, which is 4, that in parentheses, minus, then -1 cubed, which is -1, minus -1 squared, which is +1, so minus +1, right? So now this is just 4 minus -2, which is 6. So this procedure is really algebraically simple. You just integrate normally, and then we just add numerical values. But you just need to be careful about the positive and negative signs, because there'll be little tricks like -1 minus +1, which is just -1 minus 1, which is -2, right? So you just got to be careful with the subtraction, and we got to make sure to put our parentheses right. So that's pretty much the basic of how to do a definite integral problem. Alright, so now that we covered the basics, let's move on to a different type of problem, shall we? Now let's add some trigonometry in here. Now we're going to try to find the integral from pi over 3 to pi over 2 of the tangent of theta over 2 times the secant squared of theta over 2 d theta. Alright, so right off the bat, I think we could all see that there's a u substitution involved. First, this is just anti-differentiation. You should know how to do this already. So u equals tangent of theta over 2. And then we try to find du, which in this case, once we use chain rule, is secant squared theta over 2 times 1/2. So it's 1/2 secant squared theta over 2. So now when we plug in the actual u values, you get that it is the integral from pi over 3 to pi over 2 of u times 2 du, because that's the secant squared. So times 2u du, right? So we could just put a 2 out on the top. So it's pretty much 2 integral of u du. From pi over 3 to pi over 2, right? And that's nothing, sorry for the reflection. Okay, so now once you have that, all it is nothing but 2 times u squared over 2 from pi over 3 to pi over 2. And now once you plug in whatever the actual u value is, you get that it is 2 times, what's u? U is the tangent of theta over 2. So it's tangent squared of theta over 2 over 2. Sorry, yeah, 2 times that from pi over 3 to pi over 2. And then once we simplify that a bit, we find out that it's nothing but 2 divided by 2, 2 divided by 2 times the tangent squared of theta over 2 from pi over 3 to pi over 2. So in the end, that's what we find it is. And the 2 over 2 is obviously 1, right? And we could simplify that into, okay, so we get tangent squared of theta over 2. So we first plug in a pi over 2 in there. So it's tangent squared of theta over 4, which is 1, minus, we'll see we have pi over 3. Tangent squared of tangent squared of pi over 6, which is nothing but 1/3. Then we get the answer to be 2/3, which is, our final answer. Yes, that is the answer. So it's just nothing but a matter of simplification, as we can see. So that's how you do definite integrals with u substitutions involved, right? Just you need to make sure not to mess up, right? So that's that. Alrighty, just get that cleared up. Now, the next example we'll be looking at is how to do definite integrals in the parametric form. Alright, so our question here is going to be to evaluate from -2 to 2 of y dx. In this case, we're given that y equals 2 cosine theta, right? And we get x equals 2 sine theta. Now, the first thing you need to do is notice that there's a dx involved in the equation. Therefore, we need to find dx since we know the value of x. The derivative of 2 sine theta is 2 cosine theta d theta. Now, in the end, what we're going to do is just plug these x, y, and dx values right into there. But there's one really important step that's special for parametric equations that we have to take note of. By the way, this is example 3, sorry. Right, there's one special step that we need to take note of, and that is we need to look at the limits of integration very carefully. So now, in this case, since we're going to put everything in terms of theta, we have to notice that -2 and 2 are not just going to stay the same. So we need to first put -2 equal to 2 sine theta, right? Because x equals 2 sine theta. So we're going to put -2. -2 is the current x value. Now we're going to put it in the values of theta, because x equals 2 sine theta, so we put -2 equals 2 sine theta, right? Then we just solve for that. So it's -1 equals sine theta. And if we solve for that, we get theta equals -pi/2. Now this is the lower limit of integration. So we get -pi/2 to be the lower limit of integration. Now that we did -2, we need to do the same thing for 2. So now we need to make 2 equal to 2 sine theta. Yeah, then we get sine theta equals 1, right? And then we just get that theta equals pi/2, positive pi/2. This is the upper limit of integration. So now that we solved for what x, well, we're given what x and y equals, we solved for what dx is, we solved in terms of theta what the lower limit of integration is, which is -pi/2. We know what the upper limit of integration is, which is just pi/2. So now we can transform this equation into how we will solve a problem. It is from -pi/2 to pi/2 of y dx. In this case, what is that? That's 2 cosine theta times 2 cosine theta, which is y, times 2 cosine theta d theta. So let me just write that out. So it's 2 cosine theta times 2 cosine theta d theta. And if we simplify that, we get that's nothing but equal to, let's see, from -pi/2 to positive pi/2 of 4 cosine squared theta d theta, right? Now, once we arrive at there, then all we need to do is just simplify past that point, right? So what we do from there is make that, you first of all factor out the 4, right? And -pi/3, pi/2, and then we notice that cosine squared d theta is nothing but, by trigonometric identities, 1 plus cosine of 2 theta over 2 d theta, right? We first noticed that. And then once we just do some algebra simplification, we find that that equals 2 times theta plus sine of 2 theta over 2. And then we're going to make that from -pi/2 to pi/2. And then once we just do all the work and substitute pi/2 into there, and then we put that in parentheses, minus what we plug in -pi/2 into there, we get that the final resulting answer is nothing but 2 pi. Alright, so you might notice I might have skimmed over it a little bit at the end, just because that's just basic algebra, and then you should just know your trigonometric identities to do that. But the important lesson we learn here for any parametric equation is you're probably going to be given the x and y value. You're going to have to find the dx, and the most important part you shouldn't forget is to look at the lower and upper limit of integration. So, and then what you do is you make the lower limit equal to the x, which in this case is 2 sine theta, right? We make the upper limit equal to x, which is 2 sine theta, and then we solve for what theta equals. Now, theta equals negative pi over 2. That's the new lower limit of integration. Theta equals pi over 2. That's the new upper limit of integration. Then it's just basic algebra, and you just solve. So that is the parametric example of how to solve definite integrals. So we're going into some new calculus BC territory for that example. Right, now, let's see, where do we go right now? Now, we're going to be dealing with Riemann sums. Whoop-de-doo, right? So now, let's look at how to solve them. Let's say you have from 0 to 2, 0 to 2 to x cubed dx. And then you're required for 4 subintervals, yeah, 4 subintervals, and they're all rectangles. And you're asked to find the left-hand sum, the LHS, the right-hand sum, and the midpoint sum. Alright, so now let's look at how to do this. Now the first thing I recommend you do is you draw a graph. So you find that, right? This is your graph. It's from 0 to 2 of x cubed. So it's going to look something like this, right? So this is 0. Make that equals to 2, right? And now it's at 4 subintervals. So what you're going to do is, you guessed it, you're going to make 4 subintervals. So you have 0.5, 1, 1.5. Yeah? Just mark that to be safe so you're not confused. Right? If you do that, then you have, if you count, you have 4 intervals. 1, 2, 3, 4. Yeah? So now the left-hand sum in this case is going to be, again, just what it sounds like. The left-hand sum is going to be nothing there. Yeah? It's going to be that small rectangle there, that one there, and that one there. That is the left-hand sum. Since it's an increasing function, the left-hand sum in this case underestimates the area. That's an interesting point to note. Now, what's the right-hand sum? Well, the right-hand sum in this case goes like that, like that, and like that. That is the right-hand sum. So let me just label that. The left-hand sum underestimates, the right-hand sum overestimates. Yeah? Now let's find what the actual values are for each of these. Now, let's start with the left-hand sum. Now if we do the first, okay, now you'll notice that we're just trying to find the area of a bunch of rectangles here, right? So from 0.5 to 1 is 0.5. The width is 0.5, the width is 0.5. So you'll notice all the widths are 0.5. It's the length that changes, right? Now, for the left-hand sum, we'll notice that the first height is nothing but f of 0.5, aka it's 0.5 cubed is the first height. So we just write that it is 0.5 cubed, right? That's the first height that we find. The second height is just 1 cubed, which is just 1. The third height, the third height is 1.5 cubed. So we write that down. So yeah, the first height is 0.5 cubed, then it's 1 cubed, which is just 1, then it's 1.5 cubed. Those are the 3 heights that you find, right? And then those 3 heights multiplied by the width, which is always 0.5. And once you do the math for that, you get the value for the left-hand sum, which in this case is, let's see, it is 9/4. So that's the important thing you need to understand for left-hand sum. There's no first one because that's a 0. then it's 0.5 cubed, 1 cubed, 1.5 cubed. Those are the three heights. Now let's find the right-hand sum. Well, for the right-hand sum, it's very similar, except the first height is f of 0.5, aka the first height is 0.5 cubed, right? The first one. The second is, let's see, the height for this one is actually 1, so it goes 1 back, right? So it's 0.5 cubed plus 1 cubed plus 1.5 cubed, right? 0.5 cubed, 1 cubed, 1.5 cubed, and now this is 2 cubed. And all that is multiplied by 0.5, because 0.5 is always the width, right? 0.5, 0.5, 0.5, 0.5. But then the heights, in this case, there are 4 heights. Because there are 4 discernible heights at least, because the right-hand sum overestimates. For the left-hand sum, we only found 3 discernible heights, because the 4th one is 0, because there's just a line here, right? So for the right-hand sum, we find it's 0.5 cubed plus 1 cubed plus 1.5 cubed plus 2 cubed, all times 0.5, which is the constant width. In this case, we find the right-hand sum to be much larger, 25 over 4. Why is it much larger? Because we have a 2 cubed that makes it much larger, right? So now we know how to find the left-hand sum and the right-hand sum. And then you should notice that the pattern of whether it overestimates or underestimates is all depending on whether it's an increasing function or a decreasing function. That's always, and yeah, that's always one. Left-hand sum versus right-hand sum, increasing function versus decreasing function always influences whether it overestimates or underestimates. One thing that it's just my own personal trick to try to get to memorize this, is called Rio. What this tells me is if it is a, how should I put this? So if overestimates, increasing. So if it is a right-hand sum of an increasing function, it overestimates. That's what Rio stands for. But the thing is, if you just memorize Rio, if you just memorize this, you could just get everything right off the bat. As in, if it's a left-hand sum and it increases, then you could automatically know that it underestimates, because one of them is kept constant. Instead of left, it's right, right? And now, say it decreases. Say it's RHS and it decreases, then it also underestimates. Because increasing is opposite of decreasing. Therefore, right-hand sum decreasing, it underestimates. But if it's a left-hand sum and it decreases, then it overestimates. So, I don't know, it's just my little personal way of not messing up on left hand versus right hand, because sometimes I might get confused. So if you just memorize this, you're like, okay, if you see something increasing and they're asking for your left hand, then it overestimates. Right hand overestimates, left hand underestimates. And if it's decreasing, everything just switches around. So it's just a nice little way to get the left hand versus right hand differentiation, right? Alright, so that's the left hand sum versus right hand sum. Really quick tutorial on that. Let me just erase it now. Now, let's just do a really quick example with that same concept, shall we? Alright, it's a nice simple one. Let me see if I can find it really quick. Oh, whoops, what happened? Oh, there it is. Alright, just a really quick example, right? Say you have from 1 to 6 of 120 over x dx, and you want to have it with 5 intervals. You want to find the left-hand sum, the right-hand sum, and I'll explain to you what the midpoint sum is right now, actually. Alright, so let's just draw a quick style sketch of how to do this thing, right? So you have a graph like that. Now if it says 120 over x, it's one of those inverse functions, yeah? You know it's going to look something like this. Again, quick style, right? Say this is 1, say this is 6. Well, it says draw 2, 3, 4, 5, 2, 3, 4, 5. Cool? So you know that since there are 5 subintervals, yeah, and there's 1, 2, 3, 4, 5, that the width of each subinterval is just going to be 1, because it's just 2, 3, 4, 5 Just the width is always going to be 1. Alright, so this is a decreasing function. You should keep note that it's all opposite. So let's just start with the left-hand sum. In this case, the left-hand sum overestimates because it's decreasing. Remember that it switched around from the RIO, right? Because it's decreasing. Alright, so for the left-hand sum, it overestimates. So let's just draw super quick style. That is the left-hand sum. It overestimates. Now let's just quickly calculate what it is. So the width is always 1. So all we're literally doing is adding up the heights. So this is f of 1 plus f of 2 plus f of 3, etc. So what's f of 1? 120 over 1 is just 120. Plus f of 2 is 60. 120 over 2, right? F of 3 is 40. F of 4 is 30. F of 5 is 24. 120 over 5 is 24. Boom. LHS equals, add that all up, and then you get the value to be 274. That's the left-hand sum. Now let's find the right-hand sum. Now, the right-hand sum in this case is just, let me just draw it right here. Boom. The underestimating is the right-hand sum in this case. So all you do is move over the heights. You just take this height, move it over, right? So the first triangle, that's nothing but f of 2, right? So it starts from f of 2 and goes on. So it's literally just transposing this over. 60 plus 40 plus 30 plus 24. And it moves 1 over to find the last height. So in this case, you want to find f of 6. 120 over 6 is nothing but 20, right? So 24 plus 20. That's the last number. Notice how it's all correlating. 60 to 60, 40 to 40, 30 to 30, 24 to 24, right? It's all correlating, except on the left-hand sum, there's a bigger value, which is the bigger height, 120. And on the right-hand sum, there's a smaller value, 20, which is this value over here. So there are always going to be some correlations, but the left-hand sum in this case has one higher value, the right-hand sum has one lower value. And in the end, the right-hand sum total comes out to be just 174. Now, we found the left hand and the right hand. Now let's find what the heck is this midpoint sum, right? Well, the midpoint sum is exactly how it sounds. As in, you take the midpoint, like in 1.5 in this case, and you try to find the height at the middle point. So in this case, what we're trying to do is, so let's see, midpoint, let me just write it down. Midpoint sum. Midpoint, let me just shorthand this. Like, midpoint is quite literally nothing but, let's just take f of 1.5. 120, I'm not going to bother calculating, I'm just going to write f of 1.5 plus f of 2.5, right? You got where I'm going with this, plus f of 3.5 plus f of 4.5 plus f of 5.5. Right? I mean, just multiply all of this times 1 in this case. Why times 1? Because each of the widths are 1. And then that's whatever answer yields that comes out to be the answer. And a bit of common sense tells me that if I just average these two values, I'm just going to get the same value as that, right? Because it's the same thing as a midpoint sum. So that's the summary of what a midpoint sum is, right? For all of you that didn't know. So that was our review of left hand, right hand, and midpoint sums. Just look at whether it's increasing, decreasing, and whether it's overestimating or underestimating, right? And follow my Rio example to have a nice, quick way of doing that. And now, let's just quickly do a last example. Sorry for the length of the video. Super quick, right? Just call the average value. Right? So now if you're finding the area under a curve, which is what the definite integral does, right? What the area under, oh, look, a spider. Cool. Okay, so the area under a curve is nothing but 1 over b minus a times pretty much the integral. Now, this might sound like I'm making you memorize a formula, but if you just think about it, it's nothing but common sense. It says average value, so you have a graph that's shaped like really weird, right? Now, if you want to find the area under the curve from a to b, well, you get an area, right? Now the average value, when it says 1 over b minus a, that's all it's doing is nothing but, okay, let's take the subintervals between a and b, see how many intervals there are. In this case, it's b minus a, right? Remember for the previous example, when it was from 1 to 6 of 120 over x, there were 5 subintervals. Why? Because 6 minus 1 equals 5. Therefore, you could have subintervals that are whole numbers, right? Well, that's what it's doing here. 6 minus 1 is 5. B minus A is the amount of subintervals. Yeah, so it's the same thing. And then to find the average value, all you do is find the definite integral times 1 over B minus A. Then that's just that concept. It's kind of common sense, but just hopefully you get how to do that if it asks you for that. And then that concludes my lesson on definite integrals. It's just a recap of antidifferentiation with some numbers involved, and memorize how to do the parametric form. Don't forget how to do that. Thank you very much. This is Vamsi. See you later.